Hi, so we are looking at the section 4.3b homework, and we're specifically looking at problem number 2. So this one is asking us to evaluate the definite integral by the limit definition. So you may already know how to evaluate a definite integral, and you may already know how to evaluate without using the limit definition, but this one we're specifically asked in the directions to use the limit definition. So that's the route we're going to go. And you want to be mindful of that when you're on an exam, that you are using the limit definition when it calls for it. Okay, so overall, the general way that we use the limit definition, if you've been following some of these, as we look at the limit as n goes to infinity, we take the sum of an infinite number of rectangles under this curve. So we're roughly sketching what this looks like. Now when we have 1 to 6, okay. And then we're just taking each of those rectangles, and we'll talk about each of those rectangles have a height times a width, and we'll talk about how to find each of those height and widths. And then we add up the sum of all of those rectangles. So we look at it from I equals 1 to n, and then the width we refer to as delta x. That's the space, and they're evenly width rectangles. And that's going to be the distance between, so we're looking at x equals 1 to 6. So the total area that we're considering is going to be that 6 minus 1. And then how many rectangles we have? Well, we have n of them. So we have the width of each rectangle is 5 over n. So that's our width, and then our height is going to be each of the corresponding f values. So again, if you haven't looked at one of those approximation videos, I encourage you to look at that first before looking at this definition, this limit definition kind of one, because we're getting a little bit more extreme. Instead of doing a finite number, we're doing an infinite number. So we have this f, and the height of each of these is going to be this c sub I, the location of each of these lines. Now we're starting off with the left endpoint of 1. So the c sub I, we're starting off with the left endpoint of 1, and then we're going to increase it by increments that are our width. So this 5 over 1 times I. And so then we take that sum of that infinite number of rectangles and we'll apply that. So we have the sum of the height, which in this case is 5I over n, put into the f function, and then times the width, which is 5 over n. So here then we're looking at the limit as n goes to infinity. This 5 over n we can factor out of the summand. I'm just going to do that right away. And then we have this sum from I equals 1 to n. And then I'm going to go ahead and plug in this 1 plus 5 over ni into my given function, which is that 6x squared. So I have this 6 times 1 plus 5I over n squared. This is a step that a lot of people forget, and that is we have a binomial and we're squaring it. So we do have to FOIL. So kind of keep that in mind. And I can even factor out this 6 just to make things a little bit easier. I can even factor it out of the limit, but I'll keep it inside the limit, but outside of the summand, just for preference. I equals 1 to n, and then we'll expand this. So this is going to be, so 1 plus 5in squared is going to be 1 plus 10I over n. And feel free to stop the video and work this out by hand if you're not sure where this comes from. It comes from recursively distributing, FOILing, binomial theorem, whichever way you want to do that. We're just expanding a binomial. All right, so then we want to go ahead and look at, so this, again, this 10 over n, that's treated as a constant. That's 25 over n squared, that's going to be a constant. And so we just use those summation formulas to continue this. Look at the limit as n goes to infinity. We have 30 over n. And then the sum of 1 from I equals 1 to n, when I apply the summand, it's just going to be n. The sum is 10 over n. It's just a constant. We'll leave that up front. And so the sum of I from I equals 1 to n is going to be that n times n plus 1 over 2. And then we have this 25 over n squared. And then we're taking the sum of I squared from I equals 1 to n. And so that's going to be n times n plus 1 times 2n plus 1 over 6. Okay, and then we close this. Now, some things that I'm going to explore is just, what am I looking at in terms of the degree of the numerator and the degree of the denominator with some of these n's. So I can certainly factor in that 1 over n. And to make things easier, I'm going to have this limit as n goes to infinity. I'll have this 30. And then n over n, when I distribute that, I'm going to have a 1. Here in the numerator, I'm going to have an n times an n, and n squared is the degree of the numerator. And then the degree of the denominator, it's also going to be an n squared. Let's see, so we have these 10s will cancel. We'll have an n that cancels. Okay, so I have plus 5 times n plus 1 over n. When all of this is simplified, and I left that 30 out front. Let's just double check. And these n's cancel, these 10 and 2 cancel. I have an n in the denominator, n in the numerator. Okay. And then I'm going to distribute this n squared into the denominator. And we can go ahead and distribute, let's see, so x or n times n plus 1. And you can do this different ways. It is, I'm just kind of limited on space, so I'm going to cheat and use a calculator, but definitely you can expand that numerator using any theorem you want. 25 does not go evenly into 6. That's okay. We have plus this 25 over 6. And those coefficients are going to be important. We've distributed this n. So I have over n. And then we actually have that n squared. So this is going to be an n to the third. And then here in this numerator, when I expand everything, I get 2x to the third plus, oops, let's not do x, right? So I get for cheating with using a calculator, 3n squared plus n. Okay. And then this becomes the limit as n goes to infinity of 30 times 1 plus, here this is going to be 5n over n plus, and since we're going to be looking at the limit, we have 5n over n. This is just going to be 5 plus 5 over n. And then we have this, breaking it up by terms, we have a (50) over 6, n to the third over n to the third, so that's just going to be 50 over 6. And then continuing to distribute, we have this 3n squared. So this is going to be plus 75 over 6n squared. And again, I'm kind of ignoring simplifying just because we've got a lot going on. And then we have this 25n over 6n to to the third. So this is going to be 6n squared, and this should be an n. Okay. And so then when we apply the limit, of course, this 30 is going to be left out front. The limit as n goes to infinity doesn't affect 1. It doesn't affect this 5. It does affect as n goes to infinity. This is going to be plus 0. I'm going to have plus 50 over 6. As n goes to infinity, the 75 over 6n is going to go to 0. Just 150, 50, 0. And then this last term is also going to go to 0. So we get 1 plus 5 plus 50. And your arithmetics might be slightly different than mine. Again, there's a lot of not errors, but instances where you could, you got to reduce 50 over 6, you can distribute it to 30. You might have some slightly different results from me on that, and that's okay. And when you add up all of these, you should get 430, which you can check that using definite intervals if you know that method. Otherwise, that's it. Thank you.